Hi, I'm Zhen from Zhejiang University. Today, I'm excited to share with you our paper, Quantivine, a visualization approach for large-scale quantum circuit representation and analysis. The quantum computer is an upgraded and powerful version of the classical computer. It provides exponential speed-ups and significant advantages in fields like security and chemistry. Current quantum computers often use a computation model called quantum circuits to implement complicated quantum algorithms. It consists of two fundamental elements. The first is quantum bits, as known as qubits, represented as horizontal lines in the circuit diagram. These bits, similar to classical bits, represent the states of 0 or 1. We can operate qubits using quantum gates in the circuits, much like logical gates in the classical circuits. For example, we can use X gates to invert the qubit states from 0 to 1. Also, we can use gates that connect multiple qubits to perform multi-qubit operations. By arranging quantum gates in specific combinations and sequences, we can create quantum algorithms. However, as the capability of quantum computers grows, with more and more qubits being added, the representation and analysis of large-scale quantum circuits become increasingly complicated. Currently, there are two existing visualization methods for quantum circuits, but both have limitations when it comes to scalability. Many methods create readable and abstracted diagrams, but the creation process is time-consuming and prone to errors. On the other hand, automatic methods use programming toolkits to print quantum gates one by one on a plane. It's efficient and accurate, but can lead to overplotting and a lack of readability. To address these limitations, we propose Quantivine, which combines the advantages of previous methods and offers a solution for large-scale quantum circuit visualizations. Our approach takes quantum code as input and generates a series of readable and explorable quantum circuit diagrams by leveraging semantic analysis and graph visualization techniques. The first key idea behind our approach is to utilize semantics in the code. Auto-generated diagrams are often difficult to read due to the lack of explicit semantic structure and meanings. When presented a circuit diagram alone, it becomes challenging to answer questions about its constructions and connection patterns. However, by reading the diagram alongside its underlying code, the task becomes much easier. By examining the code, we can identify the building blocks of the circuit and infer their composition methods within the diagram. Inspired by this, we can extract semantics from the code to enhance the comprehension of quantum circuits. The second idea is to incorporate semantics of quantum circuits into circuit diagrams. We break down the circuit into hierarchical components based on the semantic structures. We also identify patterns within circuits using semantic meanings and create visual abstractions for these patterns. Furthermore, we design a series of novel circuit representations to uncover contextual details, such as qubit provenance, parallelism, and entanglement conditions. Before diving into more technical details, I would like to provide you with a live demo of our system. Now, we have the source code of QGAN algorithm, which is a quantum version of a popular neural network model that is GAN. To explore functionality of each part of QGAN, we can start by view the structure view, which represents the circuit structure in a tree-like format. By collapsing the components, we can see the circuit is composed of a discriminator and a generator, like classic GAN models. Additionally, there is a swap test component, which is special in quantum computing. By expanding further, we found that both discriminator and generator components consist of a unitary component and an entanglement component. We notice repeated patterns with these components, including large quantities of quantum gates. To confirm the role of these components, we are going to analyze connection patterns between different qubits. In the abstraction view, we found the unitary component includes a sequence of RYY gates connecting qubits in a linear manner. Alongside, the entanglement component involves linearly connected CRY gates instead of RYY gates. This observation leads us to conclude that the discriminator and generator have the same structure. Similar to classical neural networks, QGAN trains the parameters of gates to fit the data. In the GAN framework, both the discriminator and the generator are neural networks, thus their two quantum versions use the same model for simplicity. To verify this observation, we can highlight the discriminator, generator, and swap test components in the connectivity view. It shows that the qubits of generator are fully connected. This is designed to utilize the entanglement property of quantum physics to improve the model complexity and prediction accuracy. Also, it's notable that the swap test component entangles all qubits at the end, which sends the predictions from the generator to discriminators. For more detailed usages, you are welcome to refer our paper. Behind the scenes of Quantivine, a four-stage pipeline is undertaken. First, we compile and parse the programming code to collect metadata and semantic information of quantum circuit. Then, we decompose the circuit to hierarchical components with semantic structure. Next, we abstract the circuit by visualizing its pattern using visual abstractions. Finally, we enhance the contextual information with a series of visual representations. To evaluate our approach, we conduct a formal user study with 10 quantum experts and ask them to use Quantivine to explore and analyze circuits ranging from 30 to 99 qubits. The results demonstrated the effectiveness of our approach and visual design. The feedback from the users provides valuable insights for the future development of quantum circuit visualizations. Please refer to our paper for more evaluation details and findings. In summary, Quantivine provides an efficient approach for visualizing quantum circuits with high readability and supports groundbreaking skills by using semantics and graph visualization techniques. We believe our work has potential to lay the foundation for future research in large-scale quantum circuits by making their exploration and analysis more accessible to a wide range of researchers and practitioners.